In this lesson, we're going to consider hypothesis tests and confidence intervals with two populations. We discussed hypothesis testing in Chapter 8, all of the basics in those first sections. Now we're going to look at comparing two populations. One example, experiments with a control group and an experimental group. Are the results significantly different? Or, a better question that's exactly related to that, does the procedure or treatment actually work? For all of the two population tests, the test values are calculated in a similar way that we calculated the test values, the test statistics in Chapter 8. We have our observed value minus the expected value divided by the standard error. To give you an example, when we did a hypothesis test for a mean with unknown standard deviation, we had a test statistic t that we calculated. Observed value, that's our sample mean, minus the expected value, that's our population mean, whatever value was in our null hypothesis, divided by the standard deviation over the square root n. This is that standard error. So all of the hypothesis tests have this formula for the test statistic. Observed minus expected divided by the standard error. When we're looking at two independent means, we can use z if our sample sizes are large enough. So we have a formula for the test statistic for two independent means. We can see this test value calculation even here in our two independent means formula. We've got an observed value, the difference between the two means, the expected value, the difference between the two population means, divided by the standard error calculation. And we can see it kind of looks a little similar to our s over square root n, but there's some adding in there, and that's because we're working with two populations instead of just one. So the formula changes a little bit. We do have a degrees of freedom calculation because we're using a t distribution here, and the t distribution degrees of freedom are the smaller n minus 1 of the two populations. So we would have two different populations, n1 and n2 would be our sample sizes. Whichever one's smaller, subtract 1, that's our degree of freedom for this test. We've got a lot of notation over here on the right to tie us back to the formula so that you know what's what. So x bar 1, x bar 2, those are our sample means. S1 squared, S2 squared, those are our sample variances. N1, N2, those are our sample sizes. When we're dealing with independent means, the null hypothesis will always be mu1 equals mu2, which also means that this mu1 minus mu2 up here will always equal 0. So for our class, we're going to focus on a null hypothesis with mu1 equals mu2. Another hypothesis test that we can do is dependent means. In this event, with dependent means, we're looking at something like a before and an after. We are not choosing the samples independently of each other. For some reason, the two populations are connected. And this is what we mean by dependent means. We'll look at the average difference between the two populations, and our null hypothesis will assume that that average difference is 0. So if we're looking for some kind of before and after, and we want to show some change, we would want our claim to be the alternative, that the average difference is significant, that it's not equal to 0. And with the dependent means, the d bar is the average difference. So in this average difference, we're going to subtract all the pairs of numbers and get a difference. Instead of looking at each population independently, we take both populations together and we subtract to find a difference. And then we've got this standard deviation. This is actually a regular standard deviation formula. but we're looking at it in regards to the differences between the two samples instead of just looking at the samples. So the standard deviation, we do see it coming up there in the formula. And then for two proportions, when we're dealing with two proportions, our null hypothesis will be that the two proportions are equal. If our two proportions are equal, that means this P1 minus P2 will always equal 0. And the P1 hat, P2 hat, those are our sample proportions. And we've got another new symbol in here, this P bar, Q bar. These are the pooled sample proportion values. P bar is when we take the X values for both samples and the N values for both samples and put them together in a fraction. Q bar is just 1 minus P bar. Pretty much how we've defined the relationship between Q and P since chapter 5 in our class. And then our first sample proportion, P hat X over N, P hat X over N, second sample proportion. So you can see where the X's and the N's are coming from. And those are the three types of tests we're going to be looking at in this chapter. For our confidence intervals, we have an error for our independent means. And then that error is added and subtracted to the sample difference, the sample mean difference. For our two dependent means, if we're forming a confidence interval, we've got another error calculation here that we're adding and subtracting to that difference between the two samples. And then for our two proportions, another error calculation using z this time, and we're adding and subtracting again from that difference of the proportions. Breaking them down a little bit further, two samples are independent if we select the samples in such a way that we don't match them. They're not matched with the other samples selected from the other population. We say two samples are dependent if one sample can be used to determine members of the other sample. So for independent means, we've got some requirements, similar requirements that we've seen before for means. Random samples, sample data are independent. When the sample sizes are less than 30, we have that normal approximation requirement. And then our t-test, this is the same formula we had above, just broken down in a slightly different way. Degrees of freedom is the smaller of the two sample sizes, -1. For our confidence interval, for the difference between independent means, here we've got that error built into our inequality. So this t alpha over 2 square root piece, this is our error. And we've got the difference between the two means, between the two sample means here. Difference between the sample means minus the error, difference between the sample means plus the error. That's how we would form our confidence interval. We're just going to do a brief overview of all of these different concepts first. Dependent means are sometimes called matched pairs. A lot of times it's necessary to compare two sets of sample data that are directly related to each other. When the values are dependent, we're still going to do a t-test, but this time we're going to look at the differences. We'll denote the differences with the symbol d instead of x, just to be different. So x represents our samples, our sample values, but d represents the differences between the sample values. And then our mean of the population differences, we'll call that mu sub d, and the sample standard deviations s sub d. Sample data are dependent, and so we have a different situation for dependent means. Here we've got our test statistic, just like before that we've already talked about, and then the symbol's broken down a little bit further. We can also look at our confidence interval for the differences between matched pairs, where this t alpha over 2s over square root n is our error bound for the differences. And degrees of freedom are still n-1. Last, we have two proportions. The samples are random samples, sample data are independent. For each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. And so that's how we get this NP and NQ greater than or equal to 5 for both of the samples. And then for proportions, just like we were doing in Chapter 8 and Chapter 7 with proportions, we're going to use the standard normal distribution. We're mimicking the binomial distribution with these proportions, so we're going to use the normal to approximate. And we've got our test statistic here, and then some values that are broken out. This p bar that shows up here in the denominator is a little bit different. P1 minus P2 will always equal 0 for us because our null hypothesis will always be P1 equals P2. And then our confidence interval for the difference between proportions. We have our error bound for the proportions, z alpha over 2 square root term, and we can calculate a confidence interval. Next up, we'll do some examples.